German engineers tested a captured Sherman, then realized why they were losing the war late autumn 1943. Somewhere in Germany, inside a controlled proving ground used by the Heereswaffenamt, the Army Weapons Office, a captured American tank stands motionless on damp earth. Its olive paint is scarred, one track is damaged. The white star has been partially covered by German markings, but it is still visible beneath the mud. It is an M4 Sherman. Around it, a small group of German engineers move slowly, methodically. They wear heavy coats against the cold, not soldiers. Specialists, designers, analysts, men who helped shape the Panzer III, the Panzer IV, and now the new Panther. They circled the tank without speaking much, measuring armor thickness, examining weld seams, checking the turret ring tolerances. One man climbs onto the hull and opens the engine compartment. There is a pause. The interior is not elegant. It is not refined. It is not complex. It is simple, and in that simplicity, something unsettling begins to take shape. A realization that this machine may represent something far larger than a single battlefield encounter. Because by 1943, Germany was no longer fighting just armies. It was fighting industry. When the war began in September 1939, Germany did not possess the most heavily armored tanks in Europe. The early Panzer I and Panzer II were lightly armed and thinly protected. Yet they moved quickly. They were reliable. They were coordinated with radios in nearly every vehicle. And above all, they were used with operational cohesion. That combination shattered Poland. In May 1940, it shattered France. The German concept of armored warfare, later labeled Blitzkrieg, relied less on individual tank strength and more on mobility, communication, and concentrated force. German crews trained extensively in combined arms tactics. Armor, infantry, artillery, and air power functioned as an integrated system. But by 1941, the battlefield changed. Operation Barbarossa opened the Eastern Front, and German forces encountered the Soviet T-34 and KV-1 for the first time. Sloped armor, wide tracks, a 76.2mm gun capable of defeating most German tanks at range. The shock was immediate. German anti-tank units struggled. Panzer III and IV units required close coordination with artillery and air support to compensate. The myth of unquestioned qualitative superiority began to crack. Germany responded, as it often did, through engineering escalation. The Panther program was accelerated. The Tiger heavy tank entered production in 1942. Both were formidable machines. Thick armor, high-velocity guns, precision optics, but they were complex. The Tiger required immense resources. The Panther, though powerful, suffered early mechanical failures due to rush development. Germany's industrial base was skilled, but it was not vast. Every advanced vehicle demanded time, precision machining, specialized materials, and trained labor. Then, in late 1942, a new opponent began appearing in significant numbers. In North Africa, British and American forces deployed the American-built M4 Sherman. At first, German crews did not consider it extraordinary. Its 75mm gun was comparable to the Panzer IB's. Its armor was adequate, but not exceptional. It was taller than German designs, making it more visible. But something was different. It kept appearing. After the Second Battle of El Alamein in October 1942, German commanders noted the increasing presence of American equipment. In Tunisia, captured Shermans were inspected in the field. The tank was not revolutionary. It did not outmatch the Tiger in firepower. It did not possess the Panther's sloped armor sophistication. Yet it functioned consistently. Reports began filtering back to Berlin. American production capacity was accelerating. Factories in Detroit, Ohio, Illinois, and California were operating at a pace unseen in European industry. The United States had converted civilian automobile plants into armored vehicle assembly lines, where German tanks were often crafted in relatively limited numbers with significant manual labor. American tanks moved down production lines. By 1943, thousands of Shermans were being produced annually. German intelligence officers tracked shipment patterns. Convoys crossed the Atlantic. Tanks flowed not only to North Africa, but to Britain, to the Soviet Union through Lend-Lease, and later to Italy. It was not simply the tank itself that caused concern. It was the scale. The German war economy, even under Albert Speer's reforms beginning in 1942, struggled to match Allied output. Bombing raids targeted industrial centers. Raw materials became constrained. Synthetic fuel plants required protection. Skilled labor grew scarce as more men were drafted into combat. And still, the Shermans multiplied. Within the German high command, debates intensified. Some officers believed the Tiger and Panther would restore qualitative dominance. Others warned that technological superiority could not compensate for industrial disparity. By mid-1943, following the Battle of Kursk, German armored losses were substantial. The Panther's debut had revealed significant mechanical weaknesses. Final drive failures, engine fires, transmission strain. Against this backdrop, captured American Shermans were transported to testing facilities inside Germany for systematic evaluation. Not just battlefield inspection, formal engineering study. The question was no longer whether the Sherman was superior in individual combat. The question was why it appeared everywhere. As the captured tank rolled into a controlled proving ground under German supervision, engineers prepared not merely to measure armor thickness, but to understand the philosophy behind it. And that deeper examination would begin by comparing expectation to reality. By late 1943, the German Army Weapons Office, the Heereswaffenamt, had developed a systematic process for evaluating captured Allied equipment. Tanks recovered from North Africa, Sicily, and later Italy were transported by rail under guard. Once inside secure proving grounds such as Kummersdorf, they were catalogued, photographed, and disassembled. The engineers who approached the captured M4 Sherman did so with assumptions already in place. German armored doctrine emphasized armor thickness, long-barreled high-velocity guns, and increasingly sophisticated mechanical layouts. The Panther mounted a 75mm K-Kai 42 capable of penetrating most Allied tanks at long range. The Tiger I carried the 88mm K-Kai 36, a weapon feared across multiple fronts. German optics were widely regarded as among the best in the world. Their fire control precision was exceptional. In contrast, early reports described the Sherman as conventional. Its armor was riveted or welded depending on production batch. Its 75mm M3 gun was effective, but not extraordinary. Its silhouette was tall. Its gasoline-powered radial engine appeared, at first glance, less advanced than German Maybach designs. The expectation among some evaluators was simple. This would be a competent but technically inferior vehicle. A machine that relied on numbers rather than refinement. Yet the evaluation protocol demanded more than battlefield impressions. The Sherman was positioned over maintenance pits. Armor plates were measured with micrometers. The slope angles were recorded. Weld quality was examined under magnification. Ballistic tests were conducted against controlled armor samples. Transmission housing tolerances were compared to German standards. The first surprise was internal layout. The Sherman's interior was organized with accessibility in mind. Ammunition racks were positioned with consideration for crew reach. Electrical wiring was bundled and labeled with clarity unusual in wartime vehicles. Access panels allowed relatively rapid servicing of components. German engineers were accustomed to intricate designs. The Panther's final drive assembly, for example, required significant labor to access and repair. The Tiger's overlapping road wheels provided excellent weight distribution, but complicated maintenance in muddy or frozen conditions. The Sherman suspension system, using vertical volute springs in early models, was comparatively straightforward. It was not elegant in the German sense. It was functional. When the engine compartment was opened, attention shifted. The Continental R975, radial engine derived from aircraft power plants, was compact and modular. It did not deliver the raw horsepower of later German engines, but it was designed for interchangeability. Replacement units could be swapped more quickly than many German equivalents. German evaluators noted the production markings, standardization codes, identical fasteners used across multiple sub-assemblies. These were signs of industrial planning. Another detail drew quiet attention: the tank's radio installation. American doctrine, like German doctrine earlier in the war, emphasized communication. Shermans were equipped consistently with radios, ensuring coordinated maneuver. Test drives followed. On controlled terrain, the Sherman demonstrated reliable mobility. It did not possess the heavy armor of a Tiger, but it also did not weigh as much. Its drivetrain handled strain predictably. Its steering response was smooth. Most importantly, during repeated trials, it did not break down. This was not a dramatic revelation. It was gradual. Each test added a layer of understanding. German armored development had increasingly pursued battlefield dominance through technological escalation, thicker armor, larger guns, more complex systems. Each improvement required greater material investment, more machining hours, more specialized parts. The Sherman represented a different philosophy. It was engineered not only to fight, but to be produced in vast numbers, to be repaired in field workshops, to be shipped across oceans, to be operated by crews trained in weeks rather than months. German evaluators began compiling comparative charts, armor penetration tables, production timelines, estimated monthly output figures. The data was uncomfortable. The United States was not merely building tanks, it was building a system capable of sustaining armored warfare indefinitely. And the Sherman was the visible symbol of that system. As reports were drafted and forwarded up the chain of command, a pattern emerged. Individually, the Sherman did not surpass Germany's most powerful tanks. Collectively, it threatened to overwhelm them. And that realization would become clearer when examined from multiple perspectives. Not just mechanical, but human, tactical, and industrial. The evaluation of the Sherman did not end with armor measurements or engine trials. To understand why it mattered, German engineers had to look beyond specifications. They had to examine what the machine meant to the men who operated it, and to the system that produced it. Inside a tank, survival depends on seconds. German tank crews were highly trained, their gunners were precise, their commanders were drilled in battlefield communication, but German tank interiors, particularly in later heavy models, were tight. The Tiger's thick armor narrowed internal space. The Panther's layout, while efficient, demanded careful coordination. When German evaluators studied the Sherman's interior, they noted its relative spaciousness. The turret ring diameter allowed more freedom of movement. Controls were arranged logically. Ammunition storage, though initially vulnerable in early models, was positioned with crew access in mind. Later variants introduced wet stowage, reducing ammunition fire risk by surrounding shells with protective liquid-filled jackets. German analysts took note of the improvement. Escape hatches were large and accessible. This mattered. German battlefield intelligence already suggested that Sherman crews often survived penetrations that would doom crews in more tightly packed vehicles. The Sherman could burn, especially early gasoline-powered models, but the probability of crew escape was comparatively higher than in some German designs where ammunition storage was more exposed, or where turret egress was limited. A tank was not only steel and machinery, it was 5 men inside. And a tank that preserved trained crews extended combat effectiveness over time. Training a replacement crew required months. Preserving one required design foresight. That foresight reflected a doctrine focused on sustainability. The Panther was powerful. Its long-barreled 75mm gun could destroy most Allied tanks before they came within effective range. But in 1943, during its introduction at the Battle of Kursk, mechanical failures crippled many Panthers before they even engaged the enemy. Final drive breakdowns. Engine fires. Transmission strain. The Tiger, though formidable, required constant maintenance. Its interleaved road wheels performed well under controlled conditions, but became liabilities in mud and freezing temperatures. The Sherman's design philosophy was different. It was not built to dominate at extreme range. It was built to function daily. German engineers observed the modular construction of its drivetrain. Components could be accessed without dismantling large portions of the hull. Standardized bolts and fittings simplified field repairs. Replacement engines could be installed relatively quickly. Field reports from North Africa and Italy indicated that Shermans could endure extended operations with fewer catastrophic mechanical failures. Reliability translated into operational presence. A Panther immobilized by transmission failure was as ineffective as one destroyed by enemy fire. A Tiger without spare parts was a stationary gun emplacement. The Sherman's greatest strength was not its gun or armor. It was that it kept moving. Perhaps the most unsettling angle was not mechanical at all. It was industrial. Germany's tank industry relied on skilled craftsmanship. Vehicles were assembled with precision machining. Armor plates were carefully fitted. Engineering standards were exacting. But such standards consumed time. The United States approached tank production with an entirely different mindset. Automobile manufacturers like Chrysler and Ford applied assembly line principles to armored vehicles. Sub-assemblies were produced simultaneously in multiple facilities. Parts were interchangeable across batches. German analysts examining Sherman components found uniformity. repetition, standardization. This meant something critical: production scalability. By 1943, American factories were producing Shermans at a rate Germany could not match with Panthers or Tigers. Even Panzer IV production, though more streamlined, could not rival the sheer output capacity of U.S. industry operating at wartime peak. German intelligence assessments estimated American tank production in the tens of thousands annually. The figures were staggering. The Sherman was not over-engineered. It was deliberately engineered for volume. In that realization lay the true threat. German tank design had evolved toward technical superiority on a one-to-one basis. The American Sherman embodied superiority on a one-to-many basis, and as the war stretched across continents, the balance between those philosophies began to shift in ways that no single battle could fully reveal, because the Sherman was not simply appearing on one front. It was appearing everywhere. By the time German engineers completed their initial technical evaluations, the Sherman was no longer an unfamiliar silhouette. It had become a constant presence from the deserts of North Africa to the hills of Italy, and soon, to the hedgerows of France. But understanding why it mattered required stepping even further back. German armored doctrine had long emphasized concentration of force. Panzer divisions struck with speed and coordination, achieving breakthroughs through shock and maneuver. Yet by 1943, German units were increasingly on the defensive. In Tunisia, German formations encountered not isolated Shermans but formations equipped almost entirely with them. American armored divisions operated with standardized equipment. Replacement vehicles arrived through secure supply chains protected by Allied naval dominance. German field reports noted something critical. Shermans did not need to win every engagement individually. They needed to persist. In Italy, where mountainous terrain limited maneuver, German commanders still reported consistent Allied armored availability. Even after losses, units reconstituted quickly. Destroyed Shermans were replaced. Damaged Shermans were repaired. German armored units could not recover at the same rate. A destroyed Panther required months to replace. Spare parts were not always available. Fuel shortages increasingly restricted training and maneuver. By late 1943, tactical engagements revealed a pattern. German tanks could achieve local superiority in firepower, but they could not sustain operational momentum across extended campaigns. Shermans absorbed losses and returned in numbers. The battlefield rhythm shifted. It was no longer about the decisive duel between individual machines. It was about endurance. A tank division does not fight alone. Behind every armored spearhead stands an infrastructure of mechanics, transport columns, fuel depots, and spare parts distribution. German engineers studying the Sherman began to understand that its simplicity directly supported logistical resilience. The Sherman's standardized components meant that field workshops required fewer specialized tools. Spare parts could be shipped in bulk, knowing they would fit across multiple production batches. Damaged engines could be swapped rather than rebuilt in place. In contrast, German heavy tanks required careful handling. The Tiger's weight limited bridge crossings. Its complex suspension demanded precise servicing. The Panther's early mechanical fragility required constant attention. By 1944, Allied air superiority intensified the disparity. German supply convoys were increasingly vulnerable to air attack. Rail lines were bombed. Fuel depots destroyed. Even when replacement vehicles existed on paper, transporting them to the front became hazardous. The Sherman benefited from an uninterrupted transatlantic supply chain. American industrial centers were beyond the reach of German bombers. Convoys crossed under heavy naval escort. British ports processed incoming equipment with increasing efficiency. German evaluators could measure armor thickness. They could test engine output. But logistics could not be reduced to a single specification. The Sherman was designed not merely for combat, but for movement through a secure global supply network. Germany did not possess such a network. By late 1943, the war had become industrial on a scale unprecedented in history. The United States, protected by oceans and fueled by vast natural resources, had mobilized its economy completely. Steel production, oil extraction, automotive manufacturing all redirected toward war material. Germany, though technologically advanced, faced resource constraints. Synthetic fuel plants struggled to meet demand. Allied bombing campaigns targeted industrial centers like the Ruhr. Skilled labor shortages intensified as casualties mounted. When German engineers tested the Sherman, they were not simply analyzing a tank. They were confronting a manifestation of American industrial capacity. The data was unambiguous. In 1943 alone, the United States produced more tanks than Germany could field across multiple models combined. The Sherman accounted for the majority of that output. Quantity did not guarantee victory in every battle, but over time, it shaped the structure of the war. A Panther destroyed in Normandy might eliminate several Shermans before being knocked out, but within weeks, replacement Shermans would arrive. Replacement in Panthers would not. German armored units increasingly fought knowing that losses could not be replenished at the same rate. Operational planning became constrained by scarcity, and scarcity erodes initiative. The Sherman's true power was cumulative. It represented a war economy operating at full momentum, a system capable of absorbing losses without collapsing. A machine backed by millions of workers, thousands of factories, and secure supply lines. As 1944 approached, this imbalance would move from engineering reports to the battlefield itself, because soon German armored divisions would confront not isolated Shermans but entire armies equipped with them. And the decisive test would unfold in Western Europe. June 6, 1944. Before dawn, the English Channel was filled with ships. German radar stations detected unusual activity. Reports flowed upward through command channels, but uncertainty remained. Deception operations had clouded intelligence. Some believed the landing would come at Pas-de-Calais. Normandy seemed unlikely. Then the bombardment began. Naval artillery struck coastal defenses. Paratroopers descended inland. And by first light, Allied forces were landing across 5 beaches. Within days, armored units began moving ashore. Among them were hundreds of M4 Sherman standard gun tanks, command variants, engineer vehicles, and specialized amphibious versions. They did not arrive all at once. They came in waves, then more waves. German Panzer divisions stationed in France were formidable on paper. Units such as the 12th SS Panzer Division Hitlerjugend and Panzer Lehr Division contained Panthers and Panzer IBs. The Tiger-equipped Schwer Panzerabteilungen could still deliver devastating firepower. But the situation was already constrained. Allied air superiority dominated daylight movement. German armored columns advancing toward Normandy were attacked repeatedly from the air. Bridges were destroyed. Rail transport was disrupted. Fuel shortages limited operational flexibility. When German armored units finally engaged the advancing Allied forces, the contrast became stark. In individual engagements, Panthers and Tigers often outmatched Shermans at range. The long 75mm and 88mm guns penetrated American armor with relative ease. Allied crews learned quickly to maneuver, to flank, to use artillery and air support in coordination. But the key difference was not found in a single duel. It was found in persistence. Shermans continued arriving through artificial harbors constructed off the Normandy coast. Replacement vehicles were landed even as fighting intensified inland. Damaged tanks were evacuated to rear workshops and repaired. German losses accumulated without equivalent replacement. Panther breakdowns, already a known issue, persisted under combat stress. Final drive failures immobilized vehicles before they reached engagement zones. Recovery operations under constant air threat became hazardous. In the Bocage country, dense hedgerow terrain visibility was limited. Engagement ranges shortened. Tactical maneuver mattered as much as armor thickness. Here, the Sherman's mechanical reliability proved decisive. American armored units could maneuver repeatedly through narrow lanes and uneven ground. Vehicles that sustained track damage were repaired in field workshops. Units reorganized quickly after engagements. German commanders began reporting a troubling reality. Even when Shermans were destroyed in significant numbers, Allied formations did not appear weakened. They regrouped. They returned. Reports from July 1944 describe repeated encounters with large numbers of American tanks supporting infantry advances. German anti-guns inflicted casualties, but the volume of armor did not diminish. Then came Operation Cobra. In late July, concentrated Allied air bombardment shattered German defensive lines near Saint-Lô. Armored divisions exploited the breakthrough. Shermans advanced rapidly through weakened sectors, expanding the front. German armored reserves, already stretched thin, struggled to contain the penetration. The imbalance that German engineers had calculated months earlier was now visible across the battlefield. It was not that the Sherman was invulnerable. It was that it was replaceable. As Allied forces pushed toward Paris, German command faced a grim arithmetic. Each destroyed Panther represented not just a tactical loss, but a diminishing industrial reserve. Each disabled Tiger required resources increasingly scarce. And behind the advancing Allied front, new Shermans continued to disembark from ships. The decisive factor was no longer theoretical, it was operational. And as the summer of 1944 unfolded, the realization hardened into strategic inevitability. Because what was happening in Normandy was not an isolated campaign, it was the visible expression of industrial momentum. By August 1944, the German position in France had deteriorated beyond recovery. After the breakout from Normandy, Allied armored divisions advanced with increasing speed. The Falaise Pocket encirclement inflicted devastating losses on German forces attempting to retreat eastward. Vehicles were abandoned due to fuel shortages. Others were destroyed by artillery or air attack before they could be recovered. Among the wreckage were Panthers and Tigers machines that, on paper, remained among the most powerful tanks in the war. But power without sustainability is temporary. German armored production in 1944 had reached its highest levels of the war under Albert Speer's reforms. Factories worked relentlessly despite Allied bombing. Panther output increased. Panzer IV production continued. Even Tiger production expanded. Yet the scale still lagged behind the United States. By the end of 1944, American industry had produced tens of thousands of Shermans. They equipped U.S. armored divisions in Western Europe, British and Commonwealth forces, Free French units, and were supplied in large numbers to the Soviet Union under Lend-Lease. Germany, despite engineering sophistication, could not replicate that breadth. Fuel shortages intensified after Allied bombing campaigns targeted synthetic fuel plants in mid-1944. Even newly produced Panthers often lacked sufficient fuel for sustained training before deployment. Crews entered combat with limited operational hours. Meanwhile, Allied logistics deepened. The Red Ball Express, an enormous truck convoy system, moved supplies from Normandy beaches to the advancing front lines. Replacement Shermans flowed through ports as quickly as they could be unloaded. Damaged vehicles were shipped back, repaired, and reissued. The war was no longer defined by isolated engagements between elite units. It was defined by throughput. In December 1944, Germany launched its final major offensive in the west, the Ardennes counteroffensive, known as the Battle of the Bulge. German armored spearheads attempted to split Allied lines and capture Antwerp, hoping to fracture the coalition. Panthers and Tigers once again demonstrated formidable battlefield capability. In the opening days, surprise and concentrated force achieved local breakthroughs, but the underlying imbalance remained. Fuel shortages plagued German armored columns almost immediately. Some tanks were abandoned not due to enemy fire, but due to empty fuel tanks. Allied air power, once weather-cleared, resumed relentless attacks on German supply lines. Sherman-equipped units absorbed the shock of the offensive. Losses occurred. Tanks burned in snowy forests and frozen fields. But replacements were already en route. German commanders understood the stakes. Every lost Panther was irreplaceable in the short term. Every damaged Tiger represented months of industrial effort. Spare parts became increasingly scarce as transportation networks collapsed under bombing. In contrast, American armored divisions maintained operational continuity. Shermans were not individually invincible. German 75mm and 88mm guns could destroy them effectively. But the Sherman's presence was cumulative. When one fell, another took its place. The psychological effect became as significant as the material one. German crews entering battle in late 1944 did so knowing that even tactical success might not alter the strategic trajectory. Destroying 10 Shermans did not guarantee relief. 20 more might arrive within days. The industrial disparity translated into battlefield inevitability. By early 1945, as Allied forces crossed the Rhine, German armored resistance had fragmented. Some Panthers and Tigers still fought fiercely, but many units operated at reduced strength. Fuel was rationed, training time minimal. Mechanical reliability inconsistent due to rush production under deteriorating conditions. The captured Sherman examined months earlier by German engineers had represented a question. Now, on the fields of Western Europe, the answer was unmistakable. The war was not being decided solely by armor thickness or gun caliber. It was being decided by which nation could sustain mechanized warfare across years of attrition. And that nation was not Germany. As the front lines collapsed and Allied armor advanced toward the heart of the Reich, The consequences of that realization began to unfold. By early 1945, the imbalance that German engineers had first sensed in quiet testing facilities had become impossible to ignore. On the Western Front, Allied forces crossed the Rhine in March. Armored columns advanced into the industrial heartland of Germany itself. Resistance continued in pockets, often fierce, sometimes desperate, but no longer cohesive. German armored units were shadows of their former strength. Panther and Panzer IV production had continued into the final months of the war, but output no longer translated into effective combat power. Rail networks were shattered by bombing. Fuel reserves were critically depleted. Many newly built tanks could not even reach the front. Shermans, meanwhile, continued advancing. American armored divisions operated with depth. When vehicles were lost, replacements arrived through established supply channels. Workshops repaired damaged tanks rapidly. Spare parts were abundant. Trained crews rotated through reinforcement pools. In contrast, German tank crews increasingly fought with incomplete formations. A battalion that should have fielded 40 or 50 tanks might muster a dozen. Some units combined remnants of multiple formations into improvised groups. The issue was no longer technical inferiority. It was systemic exhaustion. German after-action reports from early 1945 describe armored engagements where Panthers achieved local successes, knocking out Allied tanks at range only to withdraw due to lack of fuel or mechanical breakdown. Tactical victories without operational follow-through. Meanwhile, Allied forces pressed forward relentlessly. In the Ruhr pocket, hundreds of thousands of German troops were encircled. Many armored vehicles were abandoned due to fuel shortages. Others were destroyed by their crews to prevent capture. The Sherman, by this stage, was not merely a battlefield tool. It had become the standard instrument of Allied ground warfare in Western Europe. Its design evolved throughout the war, improved armor casting, upgraded suspension systems such as the horizontal Balut spring suspension, HBSS, better ammunition stowage, more powerful 76mm guns in later variants. The machine adapted without disrupting production continuity. German industry, under relentless bombing, could not adapt as smoothly. Factories relocated underground or dispersed to avoid air raids. Production numbers fluctuated. Material quality sometimes declined due to shortages. Even the most advanced German designs, such as the Tiger II, entered service in limited numbers. They were formidable on paper, but their impact was constrained by logistics and reliability under late war conditions. In April 1945, as Allied armor converged on Berlin from east and west, the strategic verdict was clear. The industrial capacity that had produced thousands of Shermans year after year had sustained a continuous offensive. German armored doctrine, once revolutionary in 1939-1941, had been overtaken not by inferior machines, but by an adversary capable of replacing losses indefinitely. German commanders recognized this reality. Post-war interrogations and memoirs reveal recurring acknowledgement of industrial disparity. Technical superiority they conceded had been insufficient against mass production backed by secure resources. The Sherman had never needed to be the most powerful tank on the battlefield. It needed to be present again and again. And by the time Germany surrendered in May 1945, the cumulative weight of that presence had reshaped the outcome of mechanized warfare. But the story did not end with surrender. Because after the guns fell silent, engineers and historians on both sides began analyzing what the war had truly demonstrated. And in that reflection, the lessons of the Sherman and of Germany's response to it would endure. When the war in Europe ended in May 1945, Allied forces began the systematic examination of Germany's military industry. Factories were inspected. Design bureaus were catalogued. Engineers were interrogated. Technical archives were seized. Among the subjects analyzed in post-war studies was German armored development itself. The question was no longer how a Panther compared to a Sherman in armor thickness or gun penetration. The question was why Germany, despite advanced engineering, had failed to convert technical innovation into sustained strategic advantage. German designers had pursued excellence. The Panther's sloped armor and high-velocity gun were formidable achievements. The Tiger's 88mm weapon had earned its reputation through battlefield effectiveness. German optics were widely admired, even by Allied evaluators. But these strengths existed within a constrained industrial framework. Production complexity increased as the war progressed. The drive toward heavier armor and larger guns required more materials per vehicle. Assembly times lengthened. Maintenance demands grew. The Sherman, by contrast, embodied a philosophy rooted in balance. American post-war analysis highlighted several core principles behind its success: standardization, interchangeability of parts, ease of field repair, scalability of production, incremental improvement without halting assembly lines. The Sherman was not immune to criticism. Early models were vulnerable to certain anti-tank weapons. Its high profile drew complaints. Crews sometimes nicknamed it unfavorably due to gasoline-related fire risks in initial variants. But the overall design evolved, while production continued uninterrupted. That continuity mattered. By war's end, over 49,000 Shermans had been produced in various configurations. They had served not only with American forces, but also with British, Canadian, Free French, Polish, and Soviet units. German armored production across all models did not approach that scale for any single type. Post-war German engineers, when interviewed, often emphasized a critical distinction. Germany had optimized for individual battlefield dominance. The United States had optimized for sustained operational dominance. These were not identical objectives. One produced machines that could win duels. The other produced machines that could win wars. Historians examining wartime industrial output later confirmed what German engineers had sensed during their evaluations in 1943. The decisive factor was not merely design quality, it was production ecology. The United States possessed secure access to raw materials. Oil flowed abundantly. Steel production expanded. Civilian automobile infrastructure adapted rapidly to military needs. Germany faced blockade, resource shortages, and strategic bombing. Even after reforms improved efficiency under Albert Speer, the structural disadvantages remained. The Sherman thus became more than a tank. It became a case study in industrial warfare. Military academies in the decades following World War II studied the balance between technological superiority and logistical sustainability. The lessons extended beyond armor design. They influenced aircraft production strategies, naval construction philosophy, and Cold War military planning. The German engineers who once opened the engine compartment of a captured Sherman were trained to evaluate tolerances, metallurgy, and ballistic performance. What they ultimately encountered was something broader. They encountered a reflection of economic depth. In the final analysis, Germany had not been defeated by a single weapon system. It had been defeated by a coalition capable of producing weapons at a rate that absorbed losses faster than they could be inflicted. The Sherman was not the most heavily armored tank of the war. It did not carry the largest gun. It was not the most technologically intricate, but it was present on every front where Allied ground forces fought in Western Europe, and in that presence lay its significance. The war had demonstrated that modern mechanized conflict demanded not just innovation but endurance, and endurance required industry. As historians continue to examine the Second World War, the Sherman stands not merely as a machine of steel and rivets but as evidence of a strategic truth that reshaped global warfare. Wars are often remembered through the lens of heroes, of dramatic duels, of single machines that seem larger than life. Tigers roaring across the battlefield, Panthers piercing armor at impossible range. Yet the quiet lesson of the Sherman is far subtler and far more decisive. German engineers, in their meticulous testing, expected to find weakness. They expected to see flaws they could exploit. Instead, they found a machine that embodied a philosophy foreign to their own: simplicity, reliability, and the capacity for endless reproduction. It was not the most powerful tank. It was the most enduring. Endurance, it turned out, was lethal. One Panther destroyed 10 Shermans on a field. 100 Shermans replaced themselves, and the battlefield shifted not through single victories but through relentless persistence. The war was no longer a contest of one-on-one prowess. It had become a contest of industry, logistics, and the ability to sustain momentum over years and across oceans. The captured Sherman revealed a truth that German engineering could not deny. Precision alone could not compensate for scarcity. Technical brilliance could not overcome mass. A machine, no matter how advanced, is only as effective as the system that produces it, supplies it, and keeps it moving. In the end, the Sherman's legacy is not measured in destroyed Tigers or won battles. It is measured in resilience, in the invisible infrastructure of war, in the quiet arithmetic of numbers that German engineers first glimpsed in 1943, and that would unfold catastrophically on the battlefields of France, the Ardennes, and the Rhine. The captured Sherman was a mirror, not of American ingenuity alone, but of a new reality in modern warfare. that victory often lies not in the most impressive weapon, but in the machine that can endure, reproduce, and persist long after the moment of confrontation. It was not the tank that won the war. It was the war behind the tank.